Rules to manage the routing of high-speed signals, to avoid interference and/or crosstalk in the layout design, and to meet the manufacturing standards of the board are fundamental to the success of the final board assembly. The Constraint Manager provides a common integrated constraint definition environment for both schematic capture and PCB layout. The Constraint Manager supports definition and verification of both electrical and physical constraints within a single environment, simplifying a complex constraint entry process while improving design accuracy. Later in the design process, the actual routed trace lengths can be verified against the initial constraint definition, directly from within the constraint definition environment. So let's take a quick look how to define and verify constraints across the design flow. During the design capture stage, you would normally import a layer template from your library, where the board stack-up and manufacturing rules have been predefined. I will use the add multi-nets command to add 4 nets in the schematic. Once complete, I am then able to add the constraints. So I'll now go ahead and launch the constraints editor. Selecting these nets in the schematic will display them with their net names in the constraint editor. I will now assign the following constraints: maximum number of vias and net class assignment, which actually includes physical rules such as trace width and clearance. I will now define the rules for the differential pairs within the Constraints Manager. But firstly I will create a new group, which is called a Constraints class, to collect them all together. Naming the nets in the schematic with _n and _p will help identify them later when adding them to the named group. Their function can then be auto-assigned to be differential pairs, making this process very fast when there are many differential pairs in your design. I will now define the specific characteristics of convergence and separation distance. This is easily achieved using the spreadsheet-like functionality to drag and drop the values across multiple cells. Selecting the 4 nets, you can now see them displayed in the constraint editor as 2 electrical nets and as 2 differential pairs. With the differential pair constraints assigned, I will now implement them by routing them in PCB layout. I can launch PCB layout directly from within the design creation cockpit. Immediately, the integrated environment detects the connectivity and constraint changes that need to be brought forward. Notice the 2 amber lights in the dialog that also alerts us to the changes required. Zooming in at the top of the screen, around the net lines for the high-speed signals, I will now use the toolbar options to fan out and route the 2 differential pair groups using multiplow. That automatically adheres to the rules that I specified earlier. Adding match length constraints while in layout. Notice that the traffic light at the bottom of the screen immediately changes to amber to alert the engineer of any pending changes. Using the same constraint editing environment as the schematic, I can select and tune the nets to the defined match lengths. Viewing the differential pairs in the Constraints Manager also allows the routed trace lengths to be compared to the rule defined. This is done by loading the Constraint Manager actuals from PCB layout. This is extremely valuable on complex designs where you, the engineer, may need to review the results in order to compromise on the rule to meet 100% connectivity targets. You have now seen how constraints are applied and driven from the schematic through to PCB layout, in a single editing environment, enabling you to easily compare the layout actual routed values against the initially defined rule set.